Hello, in this video we're going to talk about the Sv39 MMU system. The Sv39 MMU system uses 39-bit virtual addresses to translate into a 56-bit physical address. And it does so by using page tables that are 64 bits. So each one of these tables has 512 of these 64-bit entries here. So let's take a look at what this is going to be inside of memory. So whenever we talk about page tables, we're talking about these tables that we are going to build in RAM. So a page table is filled with entries that look like this down here. And once again, this goes from bit 0 to 63, so that's an 8-byte or 64-bit entry. So each one of the tables looks like this. We have index 0 all the way down to index 511. So that's 512 total entries. Since every single entry is 8 bytes, that's going to give us a size of 4096 bytes or 4 kilobytes. So each one of these tables is 4 kilobytes. Now, in the Sv39 system, we can have up to 3 levels of page tables. That's where we get level 2, level 1, level 0. So we start at level 2, and then we work our way to level 1 or level 0. However, we can also have what's called a leaf. We can stop at any level. If we stop at level 2, we have a 1 gigabyte page. If we stop at level 1, we have a 2 megabyte page. And if we stop at level 0, we have a 4 kilobyte page. Now, most operating systems utilize a 4 kilobyte page. It's the most standard size that we have. What that means is, if you look at this page table entry down here, we have permission bits. For example, U, X, W, and R. So U stands for user. If the bit is set to 1, then user space can either execute, read, or write from it, depending on the rest of the bits. So for in user space, and that bit is set to 0, we don't get permission, and therefore we're going to trigger what's called a page fault. We also have the X, which stands for execute. So that means we have the ability to fetch an instruction from whatever that piece of memory is. We have write and read. So that's what X, W, and R all mean. So what we're doing is we're protecting a chunk of memory. If we have a leaf at level 2, we're protecting a 1 gigabyte chunk of memory using one page table entry. If we have a 2 megabyte page, that means a leaf at level 1, we're protecting 2 megabytes of memory using one page table entry. And finally, if we have a 4 kilobyte page, what we're doing is we're protecting 4 kilobytes of memory using one page table entry. Now, obviously, if we have 4 kilobyte pages, that means we're going to have more entries, we're going to have more tables, and we have to hand these out. So if we have a leaf at level 2, we only have one set of page table. That's one table of 4096 bytes, that's it. If we have 2 levels of pages, so a 2 megabyte page, we're going to have 2 levels. So we have one page table, and those are all going to branch to multiple page tables, each one 4096 bytes. And if we have a leaf at level 0, we're going to have even more. So a leaf at level 1 looks like that. So we can have multiple page tables. So this is level 2, this is level 1, and then that branches off as well. So usually most of the entries inside of here, remember there's 512 of them per table, most of the entries are going to be unused. But theoretically, we can actually have 512 different pointers inside of level 1, and that's each table. And there are 512 of those tables as well. So if you remember back to level 2, we have 0 through 511. So that means we can have pointers to 512 total tables. So this theoretically could be 512 tables. Okay, and then each one of those also has 512 entries. So theoretically, those can branch out as well. Now, that would take a lot of programming to do, and generally we don't need that much to map out the entire memory system that we've got. So the reason we only have a 39-bit virtual memory address is because generally we don't need that much memory. So if you think about what we're doing in RISC-V, we have like a little bit of chunk. So it's 8,000,000, and we basically protect that to 9,000,000. Now, mainly what we're going to use the MMU for is to protect the memory. So how this starts is, as you can see, all of this is going to be located in RAM. And so the question is how do we actually locate these in RAM? So if we take a look here, as long as we can find a page table entry, this PPN number, which stands for physical page number, will actually point us in RAM where to find the next page table. So as long as we can get to a page table entry, we can find the next page table. However, that's a problem for the very first level, so level 2 page table. We can't find it directly using that because it can be located anywhere in RAM. So we're going to look at a specific register. So this register is built in each one of the hearts. So each one of the hearts has this register, and each one of the hearts has its own MMU. So in this case, we're going to take a look at this bottom one here. So we have a 32-bit SATP register and a 64-bit SATP register. We're going to look at this 64-bit SATP register down here. We have 3 fields. One is called mode, which is right here. One is called address space identifier right here. And one is called physical page number, or PPN, down here. So the mode is how we turn on the MMU and tell it what type of scheme we're going to use. The only schemes available we have are off, that means no protection. We have Sv39, Sv48, and Sv57. So as you can see, it's a 4-bit field, and really the only ones that we're going to do in this class are going to be 0000, so that's off, and then 1000. So that's the Sv39 system. That's the value 8 converting from binary. So that's a 4-bit binary number. Address space identifier is for the translation look-aside buffer. So hopefully you remember what a TLB is. The translation look-aside buffer is essentially caching page tables. So as you can see, we can have a lot of these tables inside of memory, inside of RAM. So going out to RAM is actually a slow process that we don't want to keep doing over and over again. Especially, so say we're in a very tight loop and we keep going out to memory and doing something with that. If we had to translate every single time, that's going to take up a lot of time. So the translation look-aside buffer is the first thing that the MMU is going to consult. It's going to look for the address that we want to translate, and it's essentially a table that looks something like this. We have virtual address on the left-hand side, and we have the physical address on the right-hand side. If it can match the virtual address, it just has to look on the other side of the table and get the physical address. Now the problem with this is remember, we only have 1 TLB per heart. And so if we context switch from one process to the another, we don't want these 2 processes to share the same physical memory. And so generally what we do, so for example in the Intel system, anytime we write to what's called the CR3, control register number 3, that's the page table register. If we write to this register, it will invalidate every single one of the entries. And so every time we do a context switch, we flush out the TLB, which means we have to rewrite it. We're going to have what's called a compulsory miss every single time we translate from then on until we fill it back up. But then right when we fill it back up, we're probably going to context switch. So it depends on how fast we context switch as well. And so what they do is they add another field called the address space identifier. And what that does is it tags each one of the entries. And so the first thing it's going to match is the address space identifier. And then it's going to look at the virtual address and then dereference the physical address from there. So this is how we can tag the entries in the TLB. So generally what I do is I put the process identifier inside the address space identifier, and we use 1 as the kernel. So 0 has a specific meaning, so we don't really use 0. Now, if you can look at this, it's only 16 bits, so we only have 2 to the 16th number of entries, so that's 65536. And remember, 0 is special, so we only have really 65535. Now in this class, obviously we're not going to have that many processes. If you look at Linux used to use a 2-byte number to represent process identifiers, and they since have switched to a 32-bit number, and in some cases even a 64-bit number. But generally we don't have that many processes running all at once, even if they're all sleeping or something like that. So that's what we're going to use to actually tag our TLB so that we don't have to flush it every time. Now there is something that we can use, an instruction that we will flush the TLB, and we'll take a look at that and see when we use it and why we use it. Finally, we have this PPN. So remember, each one of the physical addresses is going to be 56 bits. So that's a physical address. That's why we call this the PPN, physical page number. If you realize it's only 44 bits, and that's what this is representing down here. So to actually come up with the physical address of the page table, the level 2 page table, so the first page table, we take this PPN number and we're going to left shift it 12 places. So that will make it a 56-bit number. However, if you remember, anytime we left shift by any number of places, so in this case 12, we're going to have 12 zeros at the end. So if you think about it, 2 to the 12th is actually 4096. So what does that mean? We can locate the page table anywhere in RAM, provided it's aligned to 4096. This is also called page alignment. So that means I can only have these page tables stored at certain memory locations. So it can't go anywhere and everywhere. it actually has to go to any memory address where the last 3 hex digits. So if you think about 3 hex digits, that's 12 bits. 1 hex digit is 4 binary digits. So if we had 0x, something like that, that would be aligned. However, if we had something like 0xDADBEEF, that's obviously not page aligned. So what we're going to do is we're going to take our page table, the very top of it, and we're going to right shift this 12 places before we store it into this register. So that means if there's any data in those last 12 bits, it's going to be lost when we put it in here. Therefore, we're not going to locate the page table in the correct location. So to get over that, what we have to do is we have to page align the table. It means the last 3 hex digits have to be 0. And so whenever we do an allocation, we have to make sure, okay, well, I need to keep adding until those last 3 hex digits are 0. Then I can put my page table in there. So if you remember, a page table is just simply an array of page table entries. If you scroll down here, these are the page table entries. So there's 512 of these things down here sitting in each one of these page tables. The whole goal of this system is to take, here's our input, and here's our output. That's the whole goal of the MMU, the Memory Management Unit. Take this input, which is a 39-bit virtual address, and convert it into a 56-bit physical address. Now what's going to happen is, once again, we have our SATP register. We take that PPN and left shift it 12 places. That's going to locate the very top of the level 2 page table. So what we're going to do is, remember that this goes from 0 to 511. So now the thing we have to figure out is, how do we actually index into this table? Well, that's where the virtual address comes from. So VPN, if you figure out, is 9 bits, and 2 to the 9th is actually 512. So the VPN2 here is the index into the level 2 page table. So if the virtual address, the top 9 bits, the most significant 9 bits of the virtual address, is, say, 8, then we're going to look at page table entry at index 8. So that's how we can essentially think of this as an array. So we would just call it level 2 at VPN sub 2. Okay, it's just an array of page table entries, these things down here. So this is what's located actually inside the table. So what happens whenever we dereference this 8 bytes? We're going to get something that looks like this bottom one. So the very first thing the MMU is going to check is this V bit, stands for valid. If this bit is 0, we immediately throw a page fault. That means I did not program the rest of it. Us as the operating system, we have to set the valid bit to 1 whenever we program that entry. The next thing it's going to do is it's going to look at RW and X. So there's only 3 ways we can actually do a memory access inside the RISC-V system. First way is a store. Second way is a load. And third way is what's called an instruction fetch. That's part of the pipeline cycle where we actually fetch an instruction from instruction RAM or just regular RAM if it's combined. So then what we have to do is we have to figure out, okay, can I store to it? So it's going to check bit index 2, which is the write bit. So if I have a store instruction and I'm trying to write to it, but this bit is 0, it means I do not have permission to write to this memory location here. And then that's going to flag it as 1 or 0. So let's take a look at what this is going to do based on the RW and X bits. So they mean something different if they're all 0s. Let's see if I can find it here. Might be under here. There we go. So it's normally going to look like this. Okay, so this is as we generally know it. If we have the R bit set to 1, that means I can read from it. If I have the W bit set to 1, that means I can store. So that's a load versus a store. And if I have the execute bit, that means I can do an instruction fetch on it. However, if X, W, and R are all 0s, it doesn't mean I don't have permission to do anything. It means that this page table entry is not a leaf. It means we're not going to stop there. We have to go to the very next page table. So if we're at level 2 and we have 0, 0, 0 for X, W, and R, that means now that page table entry is going to tell us where to find the level 1 page table. So looking at this, the MMU is going to look at these 3 bits. If they're all 0, then it's going to look at these PPN numbers right here. So these PPN numbers are going to be moved into position. So notice they're not in the right position in the actual page table entry. In fact, they just have to be shifted left 2 places. So the bit it starts at is bit index 10. but in the actual physical address, it needs to start at bit index 12. So that will actually be, whenever we look at this physical address, we can see that the last 12 bits are going to be 0. That should clue you into something. So what that's going to do is it's going to point to the very top of the level 1 page table. So now we're at the next level page table, and this points to the top of it. So to actually figure out, so remember, each page table has 512 entries, so 0 through 511. So to figure out which one of these entries to dereference, we're now going to look at VPN sub 1. And that will tell us which one of these page table entries we need to look at. And once again, the MMU is going to do the exact same thing. It's going to dereference one of these entries, one of these 8-byte entries. Look at the VBit. If it's set to 1, that means it's valid. We can look at it. Then it's going to look at RW and X. If all 3 are zeros, that means we have yet another level of page tables. So let's assume that we saw and they're all 3 zeros. So once again, we're going to look at PPN 2. We're going to move that into place, PPN 1 into place, and PPN 0 into place. And that will point to yet another page table. This is the level 0 page table. Now we are required to have a leaf at level 0. That means either the R, the W, or the X bit must be set to 1. So once again, this is a page table filled with 8-byte PTEs down here, page table entries. And we have 0 through 511 index. And this has 512 entries. So once again, we look at VPN 0 this time, and that's going to tell us which one of these entries to look at. Once again, each one of the entries looks like this. So we're going to look at the VBit. Is it valid, yes or no? If it's not valid, we go to a page fault, and that will trap us into our operating system. Now, since we're at level 0, we are required to have one of these bits, or more than one of these bits, set to 1. The only thing that's forbidden is that it's 000. If it's 000 and we're at level 0, we're going to page fault. So now that we're at level 0, and we don't have a pointer to the next level of page tables, what we're going to do is we're going to actually check these bits. So if we're doing a store, the W bit must be set to 1. If we're doing a load, the R bit must set to be 1. If it's not, we're going to page fault. If we're doing an instruction fetch, the X bit must be set to 1. If we're in user mode, this must be set to 1. Otherwise, it's considered supervisor mode or machine mode. So the kernel versus the user, if we set that bit to 1, then user mode has access to it. If we set it to 0, if the user mode tries to get to it, it's going to page fault. So G stands for global. So if you remember back to that address space identifier, the ASID, a global page means that it belongs to all address space identifiers. And that address space identifier is labeled 0. So in the TLB, if it's labeled 0, that means everybody has access to it. So it doesn't do a match of the address space identifier at first. So that's what a global page means. Then we have these 2 bits, D and A. So A stands for accessed. So what's going to happen is anytime a page is accessed, read from or written to or fetched from, the CPU, the actual heart, is going to set that to the 1. So the actual heart actually goes into memory and writes a 1 into the access bit. However, we have this, which stands for dirty. So what that means is anytime the memory address is changed, so that's anytime we do a store, the CPU, the heart, is going to set this to 1. So we can actually look at this. If D and A are both 1, that means that memory address was written to. If D is set to 0 and A is equal to 1, that means we either read from it or we did an instruction fetch from that. So now that we've got all the bits set up, we haven't page fault at this point. Now we have to actually calculate the physical address. So once again, what's going to happen is PPN 2 is going to be moved into this location. PPN 1 is going to be moved into this location. PPN 0 is going to be moved into this location. So now I've got that 3 field. But now what we have to do is calculate the last 12 bits. Well, what the MMU is going to do is it's going to take the last 12 bits of the virtual address and move it directly into here. So no matter what level we have a leaf at, we always leave the last 12 bits untranslated. It's copied directly from the virtual address. So let's take a look if we have a leaf at level 2. So if you have a leaf at level 2, remember the page table is pointed to by the SATP register, and it points to the level 2 page table, and this has 0 through 511. Once again, VPN 2 is going to point to which one of those entries we have. And whenever we dereference that entry, remember, if we have XWR set to 0, that means we're going to go to the level 1 page table. However, what if the X bit is set to 1? All of them are set to 1. That means we have a leaf. That means the PPN points to the actual translation instead of the next page table. Well, because this is a leaf at level 2, the only thing we're going to copy from the page table entry is PPN2. So that will get copied from the page table entry into the physical address. Everything else is copied directly from the virtual address. Now, if you think about it, it starts at bit index 30. And if we do 2 to the 30, that's around 1 gigabyte. Hence the name 1 gigabyte page. So we translate everything but the last gigabyte of it. So to get to the next page, something has to change here. So remember, any of these, actually it's the virtual address, so any of these bits right here that change is going to change which one of those entries we're going to look at. If we're at a leaf at level 0, any of these change will not change which entry we're looking at. So remember, the granularity is what we're talking about. Leaf at level 2 is a gigabyte page. That means one page table entry refers to an entire gigabyte of memory address space. A leaf at level 1 is a 2 megabyte page. So 2 to the 21st is 2 megabytes. And that means that a one page table entry is going to protect or translate into 2 megabytes worth of memory. And then finally, remember, VPN 0 is a 4 kilobyte page, and 2 to the 12th is 4 kilobytes. So the page table level, if we have a leaf at that level, that determines how much information is coming from the physical address versus how much information is coming from the virtual address. We always have at least 12 bits coming through there. Now, we might have more depending if we have a leaf at level 2 or level 1. If we have a leaf at level 2, we're going to have 30 bits copied directly from the virtual address. If we have a leaf at level 1, we're going to have 21 bits copied directly from the virtual address. And if we have a leaf at level 0, we're going to have 12 bits copied directly from the virtual address. So essentially what we're doing is the page level tells us what is going to come from this page table entry, this PPN right here, and what's going to come from the virtual address up here. So essentially that's what the MMU looks like. So that should give you some information on how the actual MMU works. The next video I'm going to do is how do we actually program this from the operating system side. So in this video, we saw what the MMU looks like, how it works from its perspective, and now we're going to look at it from the operating system's perspective, because now we want to program this thing to actually translate the virtual address we give it to the physical address that we give it. Thanks for watching.